right, well, over the last few videos, you guys have been watching, you've been very focused on really two main topics. One is about changing equations from polar to rectangular and rectangular back to polar, and some of the polar graphs that are out there. The topic that I'm going to be talking about in 6.5 is really going to be related to a interdependence of rectangular and polar still, but we're going to be really talking about complex numbers. So we're going to bring back the old information about I and the imaginary numbers, and the imaginary number system that worked in rectangular also works in polar too as well. So it's just to try and make sure that there's consistency between both different types of mathematics. Now, these review questions that are listed right here, I'm going to go through them very, very quickly. I'm not going to be spending a ton of time here, except for in the places where I really need to. So like saying, for instance, what's sine of a double angle? That's an identity. Remember those identities back in the past. That's 2 sine x cosine x. That comes from an identity sheet. It's just helping you remind yourself of stuff that you should have learned in the past. Solving for all the different values of a deal. This is all going to be based on unit circle information. And the reason why it's in these review questions is because the unit circle hasn't gone away. It's just time for us to make sure that we really reflect on it and know what we're talking about. Cosine is 321, and also ASTC comes into play in this. And we've written this so many times that it should really be old hat. That would mean that cosine happens to be at pi over 3. It's positive in the first and fourth quadrant, which would mean that the answer should be pi over 3 and 5 pi over 3. And these kind of should be automatic kind of questions that you should be tackling at this point in time. Number 3 really revolves around the idea that what you learned in previous sections of 6.4 about how do you change something that is in polar and change it into rectangular. Well, in this particular case, what you would do is multiply each side by r. So this is a multiply by r on each side. And we end up making r squared is equal to r cosine theta. Mr. Leesman outlined several different techniques that you need to have for those. There's usually 4 of them. And this is one of them, multiplying each side by r. That would make this x squared plus y squared, because that's another name for r squared. And r cosine theta happens to be x. And as soon as it's in x's and y's, it's in rectangular form. Okay? I really pertains to the idea that we're talking about now. And the idea of I means that it's imaginary. But its purpose is that I was invented to deal with the consideration of the square root of -1. So in a complex number system, we've seen them many in the past, where x and y are real numbers and I is the imaginary part of what we're talking about, and it also is, or if we want to think about it, is the square root of -1. Now, what we're going to get to is that de Moivre's idea, or polar complex ideas, are based on the fact that we can actually plot polar complex numbers and plot them on a complex plane. Now, what they mean by that is that we would draw an axis, and we would really think of this being the real axis and this being the imaginary axis, and then we should be able to absolutely draw something like 3 plus 2i, and where it would be located on that graph. It'd be 3 units in the real and 2 units in the imaginary. And it'd be a dot located in that particular spot. Okay? Now, these particular spots, location-wise, are important to be done here because they can also be done not only in rectangular, but we can also start to talk about these in polar notation when we start thinking about the graph having circular radiuses and angles that are going on with those. Now, before we tackle that, let's first talk about what the absolute value of a complex number is, too. If I said I wanted the absolute value of a plus bi, when I say something about the absolute value of that, I'm really pertaining to the idea of a distance to that point. Now, the reason why this comes up in this particular concept is that distance right there, if we think about the actual triangle that's being made in the complex format in that location, happens to be the hypotenuse. But we wouldn't really call it the hypotenuse in polar, we would call it r. Yeah, exactly. So what we're really dealing with here is the distance to that particular point, and that distance would be measured by taking the Pythagorean theorem of a squared plus b squared, and this is technically r is really what you're really finding. So when they ask you for the absolute value of a complex number, yeah, you're really finding the distance to that point, or the radius. The other part that you might be asked to also find would be what's referred to as the argument of a complex number. Now the argument is nothing more than a fancy way of saying find the angle, or theta, that's made between that and its positive real axis. So to find that angle from a plus bi situation, you would take the inverse tangent of b over a. You've got to find the angle that's going on there. That makes sense that it's b over a, and you're taking the inverse tangent to find that angle. Be cautious here, though. You have to pay attention to the quadrant that it's in. So what quadrant are you actually sitting in? So like a question like this one, if I did b over a, I know I'm in the first quadrant, and the inverse is going to give me that. But if it was something in the third quadrant, I would want that argument to actually extend all the way over here to the third quadrant. And the inverse is only going to give you an answer in the first and the fourth, so you'd have to add on your pi or subtract it from pi to get the correct deal. Now we're going to practice that a little bit, so that'll make more sense in just a minute, okay? Now, plotting each one of these complex numbers on the complex plane and then finding their absolute value and their argument, which means find their r and find their theta. That's really what they're basically saying right here. So don't be surprised by that statement. Now 3 and 4i would be 1, 2, 3 and 1, 2, 3, 4. It'd be over here in quadrant 1. This is your a value that you're basically looking at, letter A, let's just say. Okay. Now, if I want to, I would probably write down that this is in quadrant 1 too, because that'd be very helpful for me to remember to get what I'm looking for. So if I wanted the absolute value, that's the first one that we're going to calculate, is the absolute value. That would mean that I'm just taking the square root of 3 squared plus 4 squared, and that would be 9 and 16, and the square root of 25, which is 5. There's your answer for the distance to get to that spot. Okay? The next one would be to actually find theta, and that theta would be the inverse tangent of b over a, which is 4 over 3, and this is going to actually be something you need to calculate on your calculator. All right, so calculator at the ready. Here's what we're going to get. I'm going to pause just a second. Sorry about that, guys. I'm really popular. Let's see what I was doing here. Oh, inverse tangent of 4 divided by 3. And before I even go down and punch this button on this one, I'm going to make sure my answer is in radians, because that's going to be super important to make sure that it's measured correctly. And let's see what kind of number we get. Oh, 0.93 radians. And that is exactly what we were expecting to see there. Makes sense. It's going to be 5 units out because of its radius, and it's 0.93 radians, so it's less than pi over 2. All right? Now, let's keep trying these so to make sure that we get the idea. I'm going to do them in different colors so that you can see what's going on. 2 and negative 2 would be in the fourth quadrant, so let's keep that in mind as we calculate the inverses. And if I want the radius of this, I would do the square root of 2 squared plus negative 2 squared, and that ultimately would give me the square root of 8, or 2 root 2 in this particular case. That's the actual radius in that. And then if I wanted the angle, sorry, I'm going to have to put it over here. Angle is going to be the inverse tangent of negative 2 over 2, which is really the inverse tangent of negative 1, and that would be negative pi over 4, but we want to make sure that our answers for it are in the first revolution, so another name for that would be 7 pi over 4. And that would be your 2 individual answers for part B. Part C, 3i. If I just did something that was on an axis, like 3i would be sitting up here at 3i, then my answer to that would be expected that the distance would be the square root of 0 squared plus 3 squared, which would end up giving me just 3. And the angle that that's on is really not necessary to even use the inverse tangent on. I just realized that theta would be at pi over 2 because it's going straight up. All right, so keep in mind if you get ones that are on the coordinate axes, we're talking 0, pi over 2, pi, and 3 pi over 2, and are relatively easy to match up. Now, the reason why we talked about all of those is because each of those thetas and r's that you're basically talking about up above are related to being able to write the polar complex version of a complex rectangular. So working with complex numbers in polar can sometimes make things easier. Now, I know it doesn't seem like they'll make things easier, but they can than working with something that's in rectangular form. So how could we actually take a complex number in this and write it in r's and theta? Well, keep in mind that you have another name for x's, and x's are what are referred to as r cosine theta. And you have another name for y's, and y's are written as r sine thetas, and those were very prevalent in the previous sections. And finding r and finding theta can be done by using things like tangent of theta is equal to y over x, and you found things like finding r, and so forth. So all of those exchanges are really important to help you write a polar complex value. Now, the first one I'm going to write right here is going to be 3 and 3i. Now, I'm just going to get a little jot of what the picture should look like, 3 and 3i. We can definitely understand that it's in the first quadrant is where that point is for the polar complex. Now, if I want to write it in polar complex, what I need to do is basically rewrite the x and the y that are inside there in terms of polar complex. So another name for that right there would be an r concept. So I'm going to think of this as r cosine. The way you write a polar complex is going to be r cosine theta and added to I r sine theta is the way that they're going to be written as a polar complex. I'm just saying x plus bi or whatever, yi, whatever way you want to think of it, okay? Now, what I need to do is be able to fill in these particular concepts. Well, r is not hard to find because that is basically the distance from the origin to that point, or the absolute value of the rectangular, or better yet, the square root of 3 squared plus 3 squared, which is going to end up being 3 root 2. Now, there's your r. You found your r value, okay? Second would be to actually find the theta that should go into this formula, which would be the inverse tangent of 3 divided by 3, and the inverse tangent of 1 is pi over 4. So the equivalent polar complex answer would be 3 root 2 cosine of pi over 4 plus 3 root 2 I sine of pi over 4. Okay? Now, putting the I just after the root, it can be delicate. Some people will put it between the root. Some people will put it in the front. But ultimately, understand, it's probably its best place is to put it right here. That's where it's really meant to be located. I hate putting it between radicals like that. But ultimately, understand that the second part is an imaginary piece, and that's the part there. Now, what you could do is pull the r value out, because it's a common GCF, and it could be written as 3 root 2 times cosine of pi over 4, and that gets rid of that where to put the I concept, and sine of pi over 4 down here on the end. This is the preferred polar complex form, all right? And we'll talk about a shortcut way we write that too as well, because it's really long and ugly, so we have little shortcut or shorthand ways of writing it. Now, let's try one that's in a different quadrant. That's -4 and -4. So 1, 2, 3, 4, and 1, 2, 3, 4. It's down here in the third quadrant. Now, the only reason I write down the quadrant value is because you got to pay attention to theta, and you'll end up seeing what I'm talking about. R would be the square root of -4 squared, and plus -4 squared again, and that's 16. That ultimately boils down to 4 root 2, all right? It's that 4590 triangle deal. Theta, on the other hand, would be equal to the inverse tangent of -4 over -4, which is +1, and that would give you an answer in the first quadrant of pi over 4. But the answer is not in the first quadrant. It's actually in the third, so the right answer is 5 pi over 4. Now, if I'm going to go ahead and write the polar complex form, it would be 4 root 2 times cosine of 5 pi over 4 plus I sine of 5 pi over 4. 5 pi over 4. Boy, that's ugly. Okay? Now, you got the idea of how to convert from rectangular to polar. The key here is find two big values, r and theta. They are the keys to being able to write the actual formula in polar complex. Now, on to the second page. How would you go the other direction? How would you go instead of from rectangular to polar? You would go back from polar back to rectangular. This is actually a little bit easier, even in my opinion. You just evaluate the function altogether and you get the rectangular form. Here's an example of what I'm talking about. You're going to start with a polar complex version of it, and then you're going to evaluate it. Now, this is where they start to discuss the shortcut. We don't like to write all of this out, so what we write is r cis theta. What that stands for is r cosine of the theta plus I sine of the theta. So we write it in a shorthand version, R C I S. That's what that stands for, and then we talk about the theta that's involved in the actual deal. So if you see it in an R-cis format, you should be just fine. Just evaluate the trig functions is what we're going to do. So if I wanted to evaluate this, I would probably take this 2 and distribute it so I could see what it was supposed to be, and then I'd be like, okay, that's 2 cosine of pi plus 2I sine of pi, and I can evaluate the cosine of pi. Cosine of pi is -1, and sine of pi is 0. So ultimately, this answer would be 2 times -1 is -2, plus, and 0 times anything would be 0I, so the answer would be -2. Okay? All you have to do is evaluate them, and you're on to the rectangular complex. Okay? Let's try it again. This would be 3 times cosine of pi over 4, which is root 2 over 2. That'd be 3 root 2 over 2 plus, and then if I did that same distribution here, it'd be 3 times root 2 over 2 again. So that's 3 root 2 over 2I. And that actually could be written all as one individual fraction or keep it separate. It really doesn't make that big a difference. I'd almost leave it like that. It makes more sense. Okay? Now, each one of those I evaluated using unit circle. Sometimes the unit circle is not always available to us, especially if things like cosine of 2.4. Well, ultimately, that is a radian, and you would need to use your calculator to figure that out. And so I'd go, okay, that must be 4 cosine of 2.4. And that answer would be something like -2.9, sorry that went away so fast, 2.95 plus, now I do it again and distribute it a second time, that's 4 times sine of that, sine of 2.4, and it's very important that your calculator is in radians when you do this, otherwise you'll get distorted answers. 2.70I, and look at that, it's in rectangular again. Okay? Now, each one of those radian values determines which quadrant that ends up being in. And that should make sense that 2.4 radians would be shy of 3.14, that's second quadrant, and this is definitely in quadrant number 2. So, think about what quadrant the radian's in, and the actual rectangular should coincide with it. All right? Now, as soon as you invent new number systems, like you invented the imaginaries, you were like, okay, now how do I do imaginaries? Well, you have to think about all the operators that work on math in general, like adding and subtracting and multiplying and dividing and powers and All the other stuff that's out there are radicals, even in that regard. So as soon as you invent any kind of new numbering system, you got to make sure the operators work on them or decipher how they do. I mean, if I was talking about imaginary numbers, I'd be like 3i added to 2i. I would just add the two together and get 5i. Okay? If I was doing subtraction, just as easy. If I did multiplication, I'd be like, oh, how do you multiply 3i and 2i? And you ended up getting this new thing called 6i squared, and that was -1. So there were reasons behind all those. Well, same thing goes here. If we invent a new complex idea that's in polar, we have to understand how do the operators work. Well, addition and subtraction are pretty straightforward. You add ideas. Products and quotients deserve a little bit of love. And what do you do if you were multiplying two R-cis ideas? Well, you end up getting the radius of the first one times the radius of the second. So you multiply the two radiuses that are in the front. That seems to make sense. But what do you do with the actual thetas on the inside? And the cosines in the inside and thetas inside here, you add the actual thetas. So in this way, it actually starts to resemble a little bit of the product rule that pertained to exponents. This would be I sine of theta 1 plus theta 2, and you add the angles together. Now, if that's the reference that you're going to use for products, quotients should be just as easy. You would take the two radiuses and divide them that are on the outside, and, yep, you're right, you would take the angles and you would subtract them just like you used to do when it came to the rule of exponents in that regard. Now, be very careful of the subtraction one for quotients. Make sure that you're subtracting the first one minus the second one, so it is capable for you to get a negative answer in for theta. That's totally reasonable. We don't care about that. So if I was going to just do some products and some quotients, this is what they basically look like. 6 times 5 would be 30, and then it says cis. Now, cis just means it's a shorthand way of writing the cosine I sine concept, and then we've got to put the theta down here on the end. Well, what I would really end up doing would be pi added to pi over 4 because it's a product, and so I'd write it as 30 cis of pi plus, that's 5 pi over 4. And that would be your product between those two polar complexes. Let's try the second one. 4 times that, that's 12 cis of, and it's nicer when it's in degrees already. We just add the two together and we'd get 42. 42 degrees. I don't know why I paused there. My brain wasn't thinking. Now, this is why we institute polar complex. Because back in the day, we would have to have actually taken this idea and FOILed it to come up with it, and remembering that I squared is equal to -1 and so forth. Now, that doesn't seem like a bad idea, but you can easily get the same concept by converting these to polar complex concepts. So 3 minus 3i would really be 3 squared, that's 18, or really 3 root 2, cis of, where would that be located? Well, 3 over and 3 down is in the fourth quadrant, and that would be the inverse tangent of 3 over 3, which would give us negative pi over 4. I'm going to call it 7 pi over 4. That would be the actual cis format for that. Now, they're really saying multiply that times 2 plus 2i, which we did up above. That was 2 root 2 cis of pi over 4. Now I can actually make that product work, and if I multiplied these two times each other, I'd get 6 times 2, which is 12, cis of pi, 2 pi, and you've got your answer in. Now, if I wanted that in rectangular, now it's in polar, I'd have to evaluate it. Now, if I go to evaluate this, you got to follow me on this, it'd be 12 cosine of 2 pi. Well, cosine of 2 pi is 1, and 1 times that would be 12. Good job. And then I would do 12 sine of 2 pi, and sine of 2 pi is 0, so plus 0i, so the answer is 12. Okay, now that seemed like a roundabout way to get there, But the idea here is that the foiling concept and the product concept would be exactly the same deal. Now, I don't think it's really showing its face as being like the best way to go right now, but in quotients, it absolutely does shine, is where this thing really starts to take off. So let's try some quotients where we subtract the angles. If I did 18 divided by 2, so you take the two of them and you divide first, cis of the angles subtracted. That'd be pi over 10 minus pi over 20. Now, pi over 10 is really 2 pi over 20, so that would mean that the answer must be 9 cis of pi over 10. And I got common denominators here, guys. That's where that came up from. Okay, that wasn't too bad. Let's try it again if it's a division. 80 divided by 40, yeah, that's just 2 cis of 220 minus 300. And this is an introduction of that negative answer that you're going to get for the theta. So 2 cis of negative 80 would be acceptable, okay? That's pretty straightforward. Now, here's where it starts to shine. Now, if I was going to do this back in rectangular, I would actually have to find the 1 plus I down here on the bottom, and I'd have to multiply by the conjugate on both the top and the bottom to evaluate it, because we can't leave imaginaries in the denominator. But it would be just about as easy to change this to polar complex. 2 plus 2i is 2 root 2 cis, oops, I'm just going to get rid of that, cis of pi over 4. And then I would be dividing that by 1 and 1 would be the square root of 2, 1 squared, add them together, take the square root, cis of pi over 4. And if I calculated that, these would divide, I'd end up with 2 cis of these two subtracted, and pi over 4 minus pi over 4 would end up being 0. And the answer here evaluated would be 2 cosine of 0. Now, cosine of 0 is 1, so that'd be 2, plus 2 sine of 0 would be 0, so 0i. So guess what? That answer is just 2. Okay? That is exactly what this conjugate one would have generated as well. And so you can kind of see that if you can change things to polar complex, you can do it just as easily as you can do rectangular. Now, what the key is to this, guys, is full-blown practice. You need to practice these products and quotients, and more importantly, you need to practice the conversions of polar to complex and complex to polar. So you get the idea of I've got to find r's, I've got to find thetas to get to a polar complex. I've got to evaluate to go from rectangular to polar. Okay, practice that. You're going to be in good shape. All right, 6.5a on its way.